So welcome to my channel on technology space with machine learning and artificial intelligence. So today's topic is covariance and correlation in digital twin. So this is the second part of a two-part series, and this is also part of this playlist of digitalization. So in the part one of this series, we have discussed various statistical parameters with respect to a smaller data set. So that data set consists of 5 data points and which is presented in the top plot in this slide. And then in that smaller data set, we were discussing several statistical properties, which include mean, variance, standard deviation, covariance, and correlation. So let's try to expand that understanding towards a large-scale data set. So here I'm considering a large-scale data set in my bottom plot, which consists of almost 1,000 data points. So in this data set, I am representing data distribution, which is Gaussian. We would discuss what is Gaussian in a more later stage in this presentation. And this Gaussian distribution is having the mean value of 10 and the standard deviation of 10. So the mean value, which has that value 10, is represented in this plot also by a red dot. So the data set itself is represented by blue dots in the same bottom figure. So when you have a large scale data set, the first thing you are interested to know what type of a distribution consist of these data, because when you're looking into a region which is blue, you don't know whether there's a single data point or there are 1,000 data points there. So to have understand on how these data being distributed throughout its range is an important concept. So to understand that, we would utilize these histograms. So generally these data distributions can be identified by histograms. So this histogram shows the frequency of user specified range for the respective parameter of the data set. So here each smaller orange block is representing some sort of a small range for the data. And then when you count how many data points within that smaller range, you would know the number of data points within that range. So the height of this each orange block representing how many data points are allocated within that smaller region. So that way you can build up these histograms. Eventually these histograms shows you the data distribution versus the frequency or the number of data points that are located in each one of these regions. So it's a pretty useful tool in a way to understand the distribution of the data. So at some point we may be interested in transforming these histograms into probability distribution. In the top plot you can see the histogram that we developed for that selected data set. In the bottom plot, you can see that probability distribution for the same histogram. So the main difference between these two figures is going to be the y-axis. One consists of the frequency and then it transferred into the probability in the bottom plot. So how we develop this probability distribution is that we consider the total area covered under this histogram and then transfer that total area equal to 1. So in any probability calculations, the probability cannot go beyond 1. So because of that same reason, we are satisfying the total area covered under this histogram, which is equal to 1. So this transformation may not be straightforward, and then I would do this transformation through a Python exercise in another video, and the link to that video will also be placed on the description of this video. So after transforming this histogram into a probability distribution, then we can utilize some sort of a smooth functions to plot an approximation to approximate that functions through into this probability distribution. So that approximation functions came out to be this bell-shaped curve, which is, I think, eventually we discuss as the Gaussian type of distribution. So let's consider that smooth function that we have developed in the previous slide with the data distribution without the histogram. So this is what I am presenting in the top plot in this slide. And then this has a bell-shaped curve. So these bell-shaped curves often we can categorize as Gaussian distributions, but there are additional requirement these curves should satisfy. So that way we can say our data distribution is somewhat Gaussian. And you have to remember this is pretty much based on these probability distributions. And The reason why we're interested in this probability distribution is like we're considering a specific data point and then we want to know what may be the probability that data point belong to a specific range within that data set. So that type of information we can extract through these probability distributions. So let's try to define what is the Gaussian distribution. Other than being a bell-shaped curve, Gaussian distribution can be defined as if a parameter follows a normal distribution with an equal number of measurements, that means values, before and after the mean value, that can be categorized as a Gaussian distribution. Of course, this is somewhat a general definition, but let's try to be a little bit more specific. Often these data distributions or the distribution of data points within this type of a distribution can be categorized with respect to the mean and the standard deviation. So if you consider the center part of this distribution, which is starting from mean value minus the standard deviation as the starting point to the end point of mean value plus the standard deviation, that means the both left and right side of the mean value with the distance of the standard deviation. So that's the region I'm talking. That should cover the 68.3% of the data. So means if to this distributions to be a Gaussian, 68.3% of the data points should be allocated within this range. So the next range we are going to consider within that bell-shaped curve, starting from the mean value minus 2 times the standard deviation as the starting point to the mean value plus 2 times the standard deviation. So that pretty much cover the range starting from left and right side of the mean value, which is with the distance of 2 standard deviations. So that range should cover the 95.5% of the data to be this distribution as approximately a Gaussian distribution. So the third condition is if you are considering a range starting from mean minus 3 times the standard deviation as the starting point to the end point of mean plus 3 times the standard deviation. So that means you are considering the left and right side of the distribution with respect to the mean value, 3 times the standard deviation range. So that pretty much cover this total area I'm talking under this specific slide. So that range should cover 99.7% of the data points in this distribution. So you can imagine if this range cover the 99.7% of the data points, that means most of the information in this data distribution or the most of the data points in this distribution should be allocated within that range. So that these features make this data distribution is a Gaussian distribution. There may not be perfect one, but often we can approximate most of these data distributions to a Gaussian if they are satisfying the conditions that we have discussed in these previous slides. So since we have defined the Gaussian distribution and then also defining the conditions that should satisfy these data sets to be a Gaussian, let's introduce the mathematical formula for a Gaussian distribution as a probability density function. So these Gaussian distributions as a probability density functions often defined with respect to the mean and the standard deviation. So the mean is represented by mu x and the standard deviation is represented by sigma x. So the Gaussian distribution as a probability density function is denoted by px, which is equal to 1 over square root of 2 phi times the sigma x and then multiplied by the exponential function of minus half times the parameter value or the data value minus its mean value divided by the standard deviation and the squared of that quantity. So this is what the mathematical formula for a probability density function as a Gaussian distribution. Kernel density estimation is another tool that you can utilize to understand the distribution of data somewhat in a smoother way. So the kernel density estimation, also denoted as KDE, is a process of estimating a probability density function of a given parameter. And there is an internal function being utilized during this calculation. And then this internal functions we are going to use throughout this course is a Gaussian distribution. So what it is doing internally, it can approximate each data point into a Gaussian distribution, and then it sum up these distributions to create this final distribution, and that turned out to be a Gaussian also. So that way you can get a smoother Gaussian distribution for your data set or for your data cluster, and that information is useful when you're doing analysis further on these data sets. So if you compare the histogram versus this kernel density estimations, you can see the kernel density estimation give you a somewhat smooth information on as a smooth function for your data set. So if you're using the histograms, often you can see some scattered regions in these distributions, but this kernel density estimation can avoid such type of situation. So you always get somewhat a nice information by utilizing the kernel density functions in your data set. Even though we are discussing this kernel density estimation for a single parameter, you would see when you're utilizing for a multiple parameter data set, that is somewhat really useful to understand the distribution of data sets, which sometimes these histograms may not represent in a proper way. So let's increase the dimensionality of our data set by introducing an additional parameter. So we already had the parameter x with the mean value of 10 and the standard deviation of 10. Let's introduce additional parameter y, which has the mean value of 2 and the standard deviation of 2. And let's assume these two parameters are having a positive correlation. So that means when one parameter increases, the other parameter also increases. But let's talk this correlation in a little bit later stage. And then we assume these both parameters behave as a Gaussian distribution. So in this figure, in these green dots, I am representing this data cluster, and the red dot is representing the mean values for both of these parameters. So the first thing we do when we analyzing data clusters or data sets, sometimes it is useful to remove the mean value from the data set. That way it simplifies the process of the analysis process. So here I am subtracting the mean value from the respective parameters and then replotting the same data set into another figure. And here you can see this data being distributed with respect to the mean value of 0 and 0 for these two x and y parameters. So let's do a KDE estimation for the same data set, which has these two parameters x and y. So this figure represents the KDE plot for the same data set, with the green dots representing the data distribution and the red dot is representing the mean values. And then the darker regions in the center represent the density of the data set throughout its own data space. So how these plots can be created, I would discuss in the video that is related to the Python exercise in this video. So if you remove the data set from the KDE plot, it would look like this. So that means the darker regions representing the more dense area and the lighter regions representing a somewhat less dense area of the data set. So it is really useful to understand the data distribution. Specifically, we're looking into the cluster structure. So this can be considered as a single data cluster that you might see in the future data analysis process. But understanding the shapes and the sizes and the distribution as well as the directions in these data clusters are really useful when you're developing a digital twin type of models. So now in the top part of this figure, you would see the data distribution as a KDE plot for the x parameter, and for the data distribution of the y parameter as a KDE plot. You can see it in the right hand side of this figure. So now you know developing this type of a KDE plots is really useful to understand the data distribution in a somewhat simplified manner. So when you're analyzing data sets with more than one parameter, you often end up with this mean covariance and correlation matrices. So let me explain what these matrices consist of. So the mean matrix, which is denoted by MXY, consists of this mean value of the x and y parameter. If you are considering a two parameter data set, that consists of the parameter of x and y. So it's kind of compact version of these two mean values of the x and y parameter under that matrix. But if we are considering the covariance matrix, which is denoted by CXY in this case, so the top left value and the bottom right value consist of the variance values for these respective parameters. So you can see the top left consists of sigma x, which is the variance for the parameter x, and the bottom right consists of sigma y, which is the variance for the parameter y. So then the rest of the two component, which is top right and the bottom left, consist of the covariance for the parameter x and y, and that is denoted by sigma xy. Since these are more symmetrical matrices, these values somewhat equal. So next is the correlation matrix, which is denoted by Rxy. So the top left component of the correlation matrix consists of row xx. So that means the correlation of that x parameter by itself, which is equal to 1. And then the bottom right consists of the row yy. That is the correlation of the y parameter with respect to itself, which is also equal to 1. So then the top right and the bottom left component consist of the correlation from x versus y. Since this is also symmetrical matrix, these two values going to be equal. And you have to remember this is a 2-parameter situation. If you have a 3-parameter, 4-parameter and high dimensional data spaces, your matrices will get expanded with respect to the number of parameters. So that way you would get different types of mean values, covariance values and correlations values with respect to that structure of these matrices. So that way you should understand how these mean values, covariance values and the correlation values are related to each other with respect to these high dimensional data sets. I mean, it will tell you a really complex picture. So you have to have some understanding of how these complex pictures can be interpreted to develop these digital twin type of models in the future. Let's try to understand the covariance versus correlation for a 2-parameter data set. These 2 parameters are named as x and y. Then you can actually expand that knowledge into a high dimensional data spaces. So here I am presenting 9 figures, but if you look into the left column figures of this slide, that consists of 3 figures. So the common thing in these 3 figures is these figures are having a somewhat similar covariance value, yet the correlation is changing. So if we consider the top figure in this slide, that consists of the covariance of 102 and a correlation of 1. So this is a perfect condition where these 2 parameters are having a positive correlation with the value of 1. So that means when x value is changing, the y value also changing and vice versa. So often we would expect this type of a data sets, but you won't get such type of a data sets. So you often get the data set which consists of this middle figure. So what has happened in this situation is I have introduced a little bit of noise or the uncertainty into the data set that was presented in the top figure. So in the middle figure consists of the same data set with additional noise. So therefore the covariance value in this data set is somewhat similar to the top figure, which is represented by 103. But the correlation has reduced drastically because due to that uncertainty or the noise that we have introduced into this same data set. So in the bottom figure, I have introduced additional data set, additional noise or the uncertainty into the previous data set. What has happened in this situation is even though the covariance is somewhat similar to the previous data set, the correlation has reduced drastically. So now we can imagine from top plot to the bottom plot when you get additional uncertainty or the noise introduced into these data or the measurements, the correlation between these parameters may disappear. So in the middle column consists of 3 figures. What has happened in this situation is the top figure consists of the situation where you have a covariance of 0. Because of that reason, the correlation also somewhat negligible. Then I introduce somewhat smaller noise into the middle figure and then higher noise conditions or the uncertainty into the bottom figure. So as you can see, even though the covariance has increased due to these uncertainties, the correlation doesn't improve much. So this type of a situation we often classified as a white Gaussian noise. So that means these data sets somewhat pretty noisy, and we wouldn't be able to extract any parameter relationships in such type of situation. So this is also an important point. When you're looking into a different data sets or data clusters, you would get a rough idea about how much useful information you can extract it out of these clusters based on these covariance and correlation relationships. So let's try to discuss the figures in the right column of this slide that consists of 3 figures. So the common thing for these 3 figures are the covariance value for these 3 figures of the data set are somewhat approximately similar, but yet having a negative value. So when these data sets having these negative values means the parameters in these data sets tend to work in opposite direction. So that means if the x value is changing or the x value is increasing, the y value is decreasing, or vice versa. So due to this negative value in the covariance, the correlation will also have a negative value. So if we consider the top figure in this column, it has the covariance of minus 102, and then it has the correlation of -1. Since the magnitude of that correlation is 1, that means a perfect relationship between the x and y parameter, but when the x value is increasing, the y value is decreasing, or vice versa. So that is what we have learned from this having negative correlation values. So in the middle figure, what I have done, I have introduced positive noise into the data set, which was presented in the previous figure. Due to that positive noise, even though if we can say its covariance values approximately similar to the previous case, its magnitude of the correlation has reduced with the negative sign. So that means the relationship between these 2 parameters are somewhat disappearing due to the uncertainty or the noise you are introducing into a data set. In the bottom figure, I have increased this noise level further, introducing additional noise into the data set, which was in the previous case. Due to this same reason, even though we can approximate the covariance value is somewhat similar to the previous case, the correlation value has, or the magnitude of the correlation has reduced drastically with its negative sign. So that means when you having a high level of noise, these parameter relationship, either it's positive or negative, disappear from these data sets. So let's try to discuss the covariance and correlations values with respect to a vector representation. In the top figure, I am using a gold color vector to show the largest covariance direction in that data set. This vector starting from the mean value of that data set. So this representation is somewhat simpler. The vector is somewhat parallel to the data distribution, and it is showing a perfect correlation as well as the largest covariance direction from that vector. But if you move into the middle figure, what is happening, I still can represent the largest covariance direction by a vector, and then there's another direction which is opposite or the perpendicular to the previous direction. So that direction is represented by a smaller vector in this situation starting from the mean value. So now you can imagine when you have a data set with somewhat low level of noise, you can actually identify the largest covariance direction and its correlation by developing this type of a vector representation by considering the largest vector direction. But when you go to the smaller vector direction, that is somewhat representing the noise level of that data set or the data cluster. But if you're looking into the bottom data set, you can see these 2 vectors getting somewhat equal to each other. So that way it is having a really low correlation as well as difficulty to identify which relationship should be defined as the actual relationship in this data set. You should remember these two vectors are representing completely opposite relationship to each other. So if you consider the middle figure, it is representing a positive correlation between x and y values from the largest vector, but if it is representing a negative correlation between the x and y values by the smaller vector. So there is a Python exercise for this video also. So the file name is demo1. This is a Jupyter notebook file. You can download it from the GitHub repository. And then, so the link is already mentioned here and with the QR code. So the video related to that Python exercise or the link into that video, I would also place under the description of this video. So hopefully you have enjoyed these Python exercises throughout these videos. So that's pretty much going to be the end of this presentation. Hopefully you have enjoyed that. So if you're still interested in these topics, please stick around. Thank you.